Hello, AP Physics Mechanics students. Welcome to our first online physics video. This topic that we're beginning now actually turns out to be the very last topic of the entire curriculum. So this is it. We're down to the last topic. It's a short topic. The topic will only include 3 lessons, 3 cases, and then from there we'll be finished with the entire AP Physics curriculum. This topic turns out to be the most sophisticated of all the topics. What that means is you're going to see some proofs here that may look intimidating, but I can assure you from years past, students have mastered this. And when you yourself master it, I think you'll see that you'll be generating some pretty intense proofs, and you'll be very proud of your results. Being able to calculate some real serious analysis that is actually college level physics. So differential equations, here we are. What it is, oh, and by the way, I should mention that this is our first video, so you can see in the Google Stream PDF file. The PDF file is the notes that we're looking at right here, scanned in so that you have great resolution. And so if you can't see this video clearly, that's okay. I would recommend opening the PDF file and either copying the notes into your notebook before we go over the notes or after, but not during. I mean, if you want to do it during, that's fine, but I think it'd be best to just, when I'm going through this, I'm going to try and go through it quickly and efficiently so that we may move a little faster than what you can copy down. So let's begin. Like I said, there are 3 cases of differential equations that we will study. And so today is the first case. Then the next video lesson will be case 2. And then the following video lesson, the third, will be case 3. And we'll be done with differential equations and all of AP Mechanics. But differential equations is actually a huge topic. We're going to spend 3 days on it, but there are courses, entire courses in college dedicated to differential equations. We're looking at a first glimpse here, and later, of course, in college you'll study in much greater detail. So what are differential equations? Well, first of all, I put here, it's a more general view of Newton's laws, because Newton's law, second law, is A equals F net over m. But it's important to realize that A is actually a derivative, dv dt, the derivative of velocity. So what Newton's second law is, it doesn't define a function. It defines the derivative of the function. And then there are entire courses dedicated to finding the original function. Something defines the derivative, and then you have to do all this math to figure out what the original function is. So in today's case, what we're going to be looking at are forces that vary with time, okay? Time-dependent forces. So in case 1, imagine you've got a force with time on a mass, and we want to find velocity and then displacement. In other words, how fast something is moving and then where it is. This is the general process we'll be going through throughout the entire topic of differential equations. 4 steps. These you have to drill into your mind because there's so many details. If you can remember the 4 steps, they're kind of like signposts to guide you through your solution. So you'll be doing this all 3 days. Step 1, set up a differential equation using Newton's second law. This is going to just show you the general idea of how it's done, then we're going to look at examples. So you say acceleration, F net over m, well, acceleration is dv dt. So here we have the derivative defined, dv dt. And then the second step is you separate the variables. And what that means is you put all the velocity terms on one side and all the time terms on the other. So that's what we did here. I took the dt, moved it to the other side, and now I have all velocity on this side, all time on that side, and force as a function of time. Then the third step, always, is you integrate both sides. So then you see that what I'm doing is I integrate the left side from my original velocity to my final velocity. Those are the limits, and I'm integrating dv. And then I integrate time from time 0 to time final, And so this dv, trivial integral, integrates to v, and then I have to plug in my limits. And then this is, depending on the function, like for example, maybe force is t to the third power. Then we know the integral is 1/4 t to the fourth, right? So, but what we don't know what force is, so basically it just generates a new function, and then we have to apply it to apply our limits to that function. And then the fourth and final step is plug in the limits and solve for v final. So again, this is just the outline, no specifics here. Step 1, set up differential equation using Newton's second law. Step 2, separate the variables. Step 3, integrate both sides. 4, plug in the limits and solve for v final. If you can get those into your memory, the next 3 days will be much easier. And then we can also, once we get the velocity as a function of time, we can realize, what we do is we realize that the velocity itself is actually a derivative. It's a derivative of x with respect to time. So we take our function that we got from the previous answer and we replace v on this side with dx dt. Then so we have our differential equation, and then we do the other 3 steps. We separate the variables, I move the dt to the other side, and then I integrate both sides. So dx just integrates to x, the most trivial integral over the limits x0 to x final. And then velocity integrates to some new function. You know how to integrate basic power functions, for example, so there'd be the answer there. And from 0 to t final. And then again, you plug in the limits and solve. The first example, I'm going to do 2 examples now of these time-dependent differential equations. The first example, let me just cover this up for clarity, is, to borrow a word from Dr. Gavioli, a baby problem. And what that means is it's going to be the simpler problem, the first most basic problem that we can apply this method to, or these methods. So it's a 2 kilogram object, experiences a 12 Newton forward force and a force of friction of 4 Newtons. It starts with a velocity of 5 and an x0, original position on the x-axis of 10 meters. And we're going to determine the acceleration as a function of time, the velocity as a function of time, and x as a function of time. What I've done here is reminding you that force diagrams are always necessary in physics. So I just sketched a little force diagram. Force of gravity is 2 times 10 or 9.8, 20. Normal force, support force matching. A forward force of 12 newtons is pulling this thing forward, and a backwards force of friction of 4 newtons. So if I calculate the acceleration as a function of time, I do forward force minus backwards force for the net force. 12 minus 4 over 2, and I get 4 meters second squared. And notice that's not a function of time. It's just a constant. It's 4. So my velocity is speeding up by 4s every second. 0, 4, 8, 16. Constant acceleration. Then the next step is part B. Once I get the acceleration, I want to now find the velocity. So what I do is I take that acceleration and I realize it's a differential equation. So that's step 1. I make a differential equation which came from Newton's laws. A is not an algebraic expression. It's a derivative. The derivative is 4. What's the function? So what I do is I do steps 2 and 3. Usually you do those together because you separate the variables. I slide the dt over to the other side with a 4, and then I integrate both sides. Remember, the velocity started at 5, and it ended at, well, we're going to find out what it ends at. And then the time, the limits are 0 to 4 seconds, 0 to t final. So we want this as a function of time. dv, trivial integral, integrates to velocity, and we're going to evaluate it for the limits from 5 to v final. 4 dt, well, 4 is a constant, so we're just integrating dt on the right side. Again, a trivial integral, which just integrates to time. And then our limit is 0 to t final. And then we, step 4, so we set up the differential equation with Newton's laws, we separate variables, integrate both sides, and then now we plug in limits and solve, step 4. So we plug in v final and 5 into the velocity expression, and t final and 0 in for time, and then we solve for V final by just adding 5 to both sides. And here we have V final is 5 plus 4t. And I just want to point out that this matches the pattern we used all the way back in Unit 2 when we learned kinematics for constant accelerations. V equals V0 plus AT. Remember, V0 is 5 and the acceleration was 4. So we could have just, boom, put that down at the start of the year. That's what we would have done. We would have just write 5 plus 4t and been done. But that is what we say the baby way of doing it, because you are taking, someone had to solve and figure out what this equation was. Someone separated the variables and integrated and plugged in the limits for you. And you just use that. Now you see, you don't need that. You can generate that formula yourself, because you know the more general, the more true way Newton's laws are expressed as derivatives. Okay? Well, the next part we want to do, if you look back at top, we got velocity as a function of time. Now we want x as a function of time. So we go on to, let's see, here we are. Okay. And, okay, this should be centered. Let's see. Yeah, it looks good. Okay, so we start with our answer for velocity that we had before, but we realize that that's not an algebraic expression. It's actually defining another derivative. Velocity is dx dt. So we replace that this way, and now we have step 1 done. We've made our differential equation. Steps 2 and 3, if you remember, are to separate the variables and integrate. So we need all time on one side and all x's on the other. We do that by just simply moving the dt to the other side. And now dx is alone. Integrate both sides. Remember, this thing started at 10 meters on the x-axis, and it's going to some final location which we're looking for. And the timer is starting at 0 and going to some final time. So the left side, trivial integral, integrates dx to x, and then the right side integrates to 5t. This 4t dt integrates to add 1 to the exponent, make t to the 1 t squared, and then divide by the new exponent, which is 1/2 now. Now, finally, after I've integrated, I can, step 4, plug in the limits and solve. So plug in x final minus 10, those are the limits there, and then t final into our function, and 0 into our function. And there we have our answer, 10 plus 5t plus 2t squared. And once again, we could recognize that, quote, baby physics formula. X equals x0 plus v0t plus 1/2 at squared. Again, why were we able to use that? Someone solved the differential equations for you for a constant acceleration, integrating twice and getting that x function. Now you don't need that someone. You are capable of going with Newton's laws and making your own formulas. But the advantage of, rather than using these algebraic formulas, is now we can do more complicated problems where the forces actually vary with time. Remember the previous example, the forces were all constant. We had forward 12, backwards 4, end of the story. But in this next example, okay, what we have is the same 2 kilogram mass with the same forward force of 12 newtons, but now we have a force of wind, that's wind if you can't see it, of 6t in the backward direction. And what that could be like is like maybe you're pedaling at 2 meters per second, v0, at x coordinate of 10, and then all of a sudden the wind starts picking up and pushing you in the, your forward, like on the front of your body. And therefore, like it's more and more backwards force because the wind is picking up and gusting more and more. So it's creating more and more backwards force with time. So we're going to want the acceleration as a function of time, the velocity at 5 seconds, and the x-coordinate at 5 seconds. 5 seconds after you're pedaling with that kind of wind, where are you and how fast are you moving? Here's our force diagram again. We have 20 down, 20 up again, gravity, normal force balancing each other out. The 12 in the forward direction, and now we have this force of friction, which is 6t in the backwards direction. So A is F net over m. So again, the 4 steps, right? So you should be thinking, pausing the video maybe and thinking, do I remember the 4 steps? Because the sooner you commit them into your mind, the easier this problem solving process becomes. Step 1, you make a differential equation from Newton's laws. Okay? So A is F net over M, forward force minus backward force over 2, the mass. And I leave the units off. Oftentimes that's what we do with these calculus problems, because then things just become very confusing, cluttering. So you're welcome to leave the units off. So I get 6 minus 3t. There's the acceleration as a function of time. But I realize again that that's acceleration is actually a derivative. So I have a differential equation, a derivative equation. Tells me what the derivative is. Again, I have to go and find what v is. I have what dv dt is, but what is v? So step 1, I made the differential equation. Step 2 and 3, you separate the variables and then you integrate both sides. So you see what I've done is, well, I guess I should move this up a little, is I have moved the dt to the other side. So there it is with the 6 minus 3t. And then I integrate both sides. Remember, the velocity started at 2. That was given in the problem. And it's going to be some final velocity later, which is what we're looking for. The timer starts at time 0 and goes to t final. So dv, again, trivial integral, integrates to v over our limits. And then 6 dt integrates to 6t. dt, again, is like dv. It just integrates to the original variable. And then this is a power. We have 3t to the 1 power. We add 1 to the exponent and make it to the 2 power, or the second power. And then we divide by that new exponent, so we get 3 halves there in the minus sign. And then we got our limits 0 to t final. Okay? The fourth and final step is you plug in the limits and solve. V final, minus 2, right? Those are the limits. And then here we put in t final into our function, both places. And then we plug in 0 in both places. And lastly, we can now solve by putting the 2 to the other side. Remember, it was v minus 2, so we bring it to the other side and all the zeros are dropped away. So now we have our function, and the reason why I didn't plug in a limit of 5 right from the start, I could have, but I knew, because I thought of the problem, that I'm going to need this as a function of time so I can do part C. But you could have put 0 to 5 seconds and not plugged in these t's and had a correct answer. But now that I have the formula as a function of time, I could plug in 5 seconds. On a calculator, punch everything in, I get negative 5.5 meters per second. So the wind is picked up so much, now the object is actually moving backwards. Even though it's being pushed forward, there's so much wind, it's actually accelerating and moving backwards. The last part, what we want is the where it is, what is its coordinate at that moment. So what we can do is, again, we have this velocity function up here. We realize that itself is another differential equation because v is actually derivative of x. And so we take the function down here and we start with that differential equation. Once again, steps 1 through 4. Can you say them in your mind? Okay, pause maybe and see if you could say them. But here they are again. Step 1, you make the differential equation. Step 2, you separate the variables and integrate both sides. That's what we got here. And then step 4, after you integrate, is you plug in the limits and solve. So here it is, step 1, differential. Step 2, I separate by moving the dt over with all the other time variables, multiply to the other side. And then my limits are 10 to v. And here I'm just going to plug in 5 seconds, so it makes it a little simpler. I could have put t here and then plugged in t and then got a formula and then plug in the 5. But since I don't need this formula anymore, I'm just going to go right ahead. For any other parts, I'm just going to go right ahead and put 0 to 5 seconds. So dx integrates to x, and then this integrates to dt integrates to 2t, because the dt integrates to t. 6t dt integrates to, add 1 to the exponent, we get t squared, and then you divide by that new exponent. So we have 6 divided by 2, which gives us 3. Okay, and then here, t to the, oops, I made a mistake in this. Okay, so this is a good thing I caught this. But basically, we add 1 to the exponent, we make this t cubed, and then we divide by that new exponent. So really what we have here is 1/2. Okay, so I'll fix that with the scan notes, and so actually 1/2, and then a 1/2 here. Okay, and then we have to reevaluate this because I evaluated without that 1/2. So again, add 1 to the exponent, make that cubed, and then divide by 3. So we have 3/2 over 3, which is 1/2. And then we plug in the limits of 5 and 0 seconds, and we get our answer. Okay, so that is the first day, lesson 1 of differential equations. Remember, there are going to be 2 more. So this, we had case 1. So when I stop this video, again, shut it down and see if you can come up with your eyes closed maybe what those 4 steps are. Absolutely critical, so that when you're solving the problems, you have these signposts, so much detail, and if you can remember those 4 steps, then you'll be in good shape for all the rest of the differential equations in our class. Okay, well, good luck with the homework, and as usual, make sure to mark in the Google Sheet any issues you have. Even if you did the homework and you have no questions, put an X in the appropriate column to let me know that you did the homework and you have no questions. Otherwise, if I see a blank, I don't really know what that means. Maybe you forgot to put your answers, what you need to see done out, or you don't have any questions. So again, mark your sheet appropriate. Okay, see you next time for our next video.